This lesson, we're going to talk about arithmetic in binary. Just to recap the last lesson, we talked about the SR latch and the D flip-flop in the last lesson, and those are memory circuits. That's on the YouTube channel. You can go reference that video if you'd like to review. So the question that we have now is, how can the CPU do stuff that's in RAM? We have all these numbers in binary, so we have a bunch of ones and zeros. What if I want to do addition or multiplication or subtraction or something more complicated? How do I do those operations in the CPU? So today we're going to talk about once I have the numbers available to me, how do I do the math? Next time in lesson 8, we're going to talk about how does the CPU make those numbers available and how does it do what I actually want it to do? It can't just guess addition or multiplication, right? It needs to have a way of knowing I need to do addition. How does it know that? So that's what we're going to answer next time. But today we're just going to establish the digital logic behind math. So again, just to recap, we can store ones and zeros. This is a registry. So maybe we have a 4-bit number here. Maybe that number is 1001, right? So each flip-flop holds 1 bit, and each bit represents a power of 2. This is how we store numbers in binary. So say we have 1001. The third bit, the highest bit, I guess I reverse the directions, it doesn't really matter, represents 2 to the third. The next bit represents 2 to the second, the next 2 to the first, the next 2 to the zeroth. So if I write 1001, bit 3 is this bit 2 is the next bit 1 is the bit after that, and bit 0 is the last bit. It goes in decreasing order in the same way that we would write decimal numbers in decimal. You just add up the bits that are ones. So in this number, we have a 1 on the 2 to the third bit and a 1 on the 2 to the zeroth bit. So it ends up being 9. If it were 1, 1, 1, 1, we would add up all 4 of those and we get 15. So what number is this? Well, again, you're just going to add up 1, that's 2 to the zeroth, plus 2, plus 8, that's this number over here, right? We skip 4, but then don't include that one. Let me do that. Don't include in red. Don't include this. And then we do include 16. So our number is going to be 16 plus 8 plus 2 plus 1, which is going to be 27, right? That's the number here. Now, these are exercises I encourage you to pause the video and do for yourself. Okay? So the first one, fifth plus fourth, ignore third and second powers, then first and zeroth, 51. Next one, 255. The last one, 170. So these are how you store unsigned numbers in binary. Sometimes the way we do 2's complement in binary is that this first digit tells us something about the sign, whether the number is positive or negative. There's some nuance as to how we handle that. It's called 2's complement is the buzzword. We're not going to get into that. It's pretty simple, but just keep in mind that sometimes the highest bit just represents the sign of the number. So now how do we do addition? Well, before we talk about math in binary, let's think about math in decimal, what we talked about back in kindergarten. Okay. So we're going to go real slow, but there's some notes that I want you to take note of as we go through the process of solving this problem. Well, first we have a 7 plus 8. That gives us 15. So we carry the 1. That term, carry, is going to be very important. We're going to have a carry bit that we need to take care of when we do the circuitry for this. Well, now we add that carry bit to 3 and 2 for the next column. It's as if we just have a third number that we're adding, right? It's not the idea of a carry dissolves. It's just a third number that's present to add. So we get 6. And it's not 16, right? It's just 6. So there's no carry digit, which is the same as saying I'm carrying a 0. So you end up getting this as the answer. So the carry is the real important point there. Let's now go to an example in binary. Well, now in binary, I have 1 plus 1, which equals 2. But we don't have 2 in binary. In binary, 1 plus 1 equals 1, 0. So I'm going to put a 0 here, and I have to carry the 1. Okay? So let's see that. I have to put a 0 there, and I have to carry the 1. Okay? Now in the second column, I just do 1 plus 0 plus 0. There's nothing special that I have a carry bit. I just have 3 numbers to add. And I get 1. And now I carry a 0. 0 plus 1 plus 0 gives us 1. Carry a 0. 0 plus 1 gets us 1, 0. So carry a 1 and put an extra 0 in front of the two numbers. Then add, and then we're done. And indeed, this gives us the right answer. 13 plus 9 equals 22, or 1101 plus 1001 gives us 10110. Okay. So the question is now, how do I make a digital circuit to do this exact same thing? That's this circuit. Now, I'm not going to pretend like it's obvious that this should work. I'm sort of just going to convince you that it does work and not motivate how you might be able to come up with this on an airplane with no phone or anything to look up. Um, it's a creative design, I guess, is the way to put it. It's not an immediately obvious design um, based on the task of addition. So we have XORs, ands, and ORs present in this circuit, and these are the logic tables for those to remind yourself. Uh, let's go through. Oh, sorry, before we go through the function of the circuit, A, B, and C are our three inputs. Recall that we had to do addition of three numbers for a given column. That's A, B, and then C being our carry. And again, what we're going to see is that there's nothing special about the carry aside from the fact that it comes from a previous bit's addition. The carry is just added as a third bit inwards. Okay. And the outputs, by the way, you have a sum. This number right here, that's going to be S. And then C out is going to be the number that we put on top of the next bit. Okay. So let's go over here. This is the full ladder demo. Let's zoom in a bit. So we have 0, 0, 0. The output is 0. I want you, before I click the switch in any of these, to just predict for yourself what's going to happen in the circuit. Draw it out. So when I turn on B, what's going to happen? Draw for yourself what each input to every gate is and try to figure out and trace the path. So I'll trace the path first. So we have a 1 here, a 0 here, and a 0 here. That means this first XOR gate is receiving 0 and 1. So this XOR outputs 1. This AND gate is receiving 0 from A and 1 from B. So this AND gate is outputting 0. What about this XOR gate up at the top right? Well, we're getting 0 from carry in, and we're getting 1 from the previous XOR gate. So this is going to be a 1 as well. Now, what about this AND gate down here, the bottom right AND gate? Well, we're getting a 0 from carry in and a 1 from the XOR gate. This is going to be a 0. This OR gate is receiving from the output of the AND gate a 0, and from the output of the other AND gate a 0, so it carries 0. Does that make sense if you just focus on the inputs and outputs? Yes, 0 plus 1 plus 0 is just 1 without any carry. And that's what we see. If I do the same thing with A, you get the same output. If I do the same thing with C, you get the same output. We're just doing A plus B plus C, where C is our carry digits. Now, what if I have two of them on? Well, now I carry a 1 and my sum is 0, right? 1 plus 1 equals 1, 0. And so we have a 1 for the carry and a 0 for the sum. What if I do B and C and are both 1? Same thing, a 1 for the carry, 0 for the sum. What about A and B? Same thing. Now what about all three? Well, then we get 1, 1, right? 1 plus 1 equals 3. 3 in binary is 1, 1. Okay, so this is a circuit that does addition. Trace the outputs for yourself if it's still confusing. Now the question remains, how do I chain these together? Well, the answer is we're just going to duplicate this circuit over and over again. So if I wanted to have a circuit that could be a 3-bit adder, first I would connect A to the right input. So I connect each bit to a single adder circuit. Then I connect B to its inputs. And then I would connect the carries to each other. So the carry out from bit 0 needs to connect to the carry out, or sorry, the carry in of bit 1. And the carry in of bit 1 needs to connect to the carry out of bit 2. Okay? So that's the wiring here. And that's why these circuits can get kind of messy to build on a breadboard. But ultimately, your output becomes the sum for 0, sum for 1, sum for 2, and then a carry on the third bit. Because if you recall in our example that we did up here, we ended up getting a carry beyond the number of bits that were in our original numbers. So that's why we have that extra carry bit. This is represented in this demo here. Notice the carry out of bit 0 goes to the carry in of the next bit. And you can just play around with this yourself and see if you get the right output. If I turn them all on, you'll see, you know, we get different outputs for the carry out. I can just mess around with things. So you should play with this yourself and see, are you able to predict the outputs correctly? Now, uh, addition is implemented in a CPU in what we call the arithmetic logic unit, ALU. The ALU has addition as one of the operations it can perform. So an actual ALU, say this is our ALU, has many operations it can contain. Maybe it has a module for addition, maybe it has a module for subtraction, maybe a module for, I don't know, even like multiplication, or like generally maybe multiplication is more nuanced, but maybe module for like XORing numbers together. So it has all these different operations it can perform. Something that we're going to talk about next time tells it what operation we want to actually use, but it's just taking inputs, doing those operations, and then giving us the output of whichever operation that we want to get the output of. So there's two inputs to the ALU in our initial simplified picture of a circuit. Oh, sorry, of a CPU. So we have RAM, and RAM is where memory is. RAM is memory. RAM is where the numbers get stored. Okay. And so say our circuit chose to look at a particular value, or sorry, not our circuit, our computer chose to look at a particular value from RAM. Say register 12, which stored 1001. Well, then that would be one of the inputs to the ALU. The other input to the ALU would be the accumulator. The accumulator is a register that is internal to the CPU. So the RAM is a bunch of registers, maybe a bajillion registers sitting outside of the CPU. That's memory. We can look at that memory whenever we need to. The accumulator is a single register, not a bajillion registers like RAM, but just one register that exists inside the CPU and is basically a place where the CPU can store a number that it needs to store while doing math. So this is kind of the wiring. A RAM is outside of the CPU and it stores numbers, many numbers. The accumulator stores just one number, multiple bits, but still just one number like 20 or 73. It just stores it in binary. And it stores that number as both the input and the output of the ALU. So I can choose as one of my operations to do addition. That I'm saying add whatever value I'm being input with to the existing value of the accumulator. In other words, if I want to do addition, what the operation I can actually do is accumulator equals the old value of the accumulator plus the value from RAM. Okay? So all of our operations on the accumulator are going to look something like that, as we'll see next time. Now, this is a preview of what computers actually look like. What the architecture we're talking about is a real architecture. It's essentially what the PDP-8 used from 1965. It was the first commercially successful computer. Okay. In 1961, IBM's Stretch implemented a somewhat similar system with multiple registers. So we talked about how there is one accumulator. Imagine we have multiple accumulators that the CPU can now use. So that was very useful. Because now we can do operations like A plus B times C plus D really easily. In this system, I have to first do A plus B, or I have to get the value of A, add the value of B, store that value, get the value of C, add the value of D, store that value, get the old value of A plus B, multiply that by my value of C times D. It's a whole bunch of steps. Here I can store A, B, C, D in my CPU itself, and I'll have to do all these store in RAM, load from RAM operations that take a bunch of time. The first microprocessor, so this is like a big computer. I think it's like $20,000 at the time. This is just a chip, this Intel thing on the left, Intel's 4004. Beyond that, the Pentium Pro in 1995 essentially brought about the idea of multiple ALUs. Again, this is an abstraction over what's actually going on. There's more, of course, to the picture, but this is essentially what it did. It gave us the ability to do multiple operations in parallel instead of only having one bottleneck single operation. And then finally, the state-of-the-art CPUs like Intel's Xeon 6 Plus Clearwater Forest. They have tons of extra modifications, like many CPU cores per chip and all these caches and other optimizations. But I say this because fundamentally, it's still a CPU. It still looks if you squint your eyes, the same as the CPU that we're talking about now. So what we're doing is really quite similar to how actual computers work, and I think that's neat for you guys to think about. And this is just context. We talked about MOSFETs and how MOSFETs become logic gates. The PDPA had roughly 1500, Intel 404 about 2300. The Pentium Pro about 5.5 million transistors. And this Intel thing, just as a rough estimate on the back of the envelope, as a back of the envelope calculation, probably over 100 billion transistors. So we have insane numbers of transistors on these chips, and that just should hopefully put in context of the amount of engineering that goes into these designs. So yeah, that's all I got. Thank you very much.